Welcome to the Roboticist Chronicles, an ARC Specialties podcast, where we get into the nuts and bolts of robots, automation, and the implications of an evolving machine workforce.
Hi, I'm Dan. I'm back. We're at the ABB booth. I've been working with ABB. You were the first robot we started integrating, man, I don't even remember how long ago. I got Doug Hickson. He's going to tell us about some of the latest stuff he's got going on with this robot here. Back in the old days, robots were only specified with repeatability, right?
Right.
Nobody talked about accuracy.
No, not at all.
Are you ready to guarantee an accuracy here?
Yeah, I can guarantee an accuracy on this robot. It's 300 microns max error, 150 microns mean error.
Microns? I've never even seen one.
Well, let's put this in English units. So 250 microns is 10 thou. So we have an average of under 10 thousandths of an inch anywhere in the robot's envelope.
Not bad.
Yeah.
And how do you do that?
How do we do it? So what we do is we take the robot in the factory. When we produce a robot, we put it in a laser calibration station. We put it under maximum load. In this case, this was a 12 kilogram arm, so we put 12 kilograms on it. And then we put it through 100 different points and laser measured it. From there, we put it through our algorithm, determined how much was related to mechanical tolerancing, deflection of the links, and compliance of the joints. We're able to reduce the error of a robot about that size of 5 to 6 millimeters down to 250 microns, or 150 microns actually on that arm. Yep.
That's pretty cool. So, way back in the day, I used to lead screw compensation, to compensate for errors in a lead screw.
Okay.
So this, in effect, is sit with 6 degrees of freedom compensation for all of this.
Exactly.
Including gravity.
Including gravity. That's the key. It's 60% of the error we see is relative to gravity. It's relative to the tool itself. Only about 40% or so is mechanical stack-up tolerance.
But this is a collaborative robot, right?
That's correct, yep.
So you've got a precise collaborative robot.
Precise and accurate. So precise meaning the repeatability can go to the same spot every single time, but then the accuracy portion of it, we can go to the exact position we commanded it relative to the robot's base.
If you rewind way back to when I picked ABB as my first robot, one of the things that I liked was the way you calculate and set up TCP, tool center point.
Right.
But way back in the beginning, it would take me half a day and a calculator.
Right, okay? Right.
And that little device right there is what impressed me years ago. Why don't you tell us what it is?
Okay, so that is the ABB Bullseye. I believe that came to market back in the mid-90s, if I'm not mistaken, so it's been a long time.
It looked a little different. It was orange. It looked like a horseshoe.
That's right, and we can get these devices a little bit more ready-made. The old ones, you had to line up the sensors, or at least we did in manufacturing, so an improvement there, more of an off-the-shelf item. It is a single laser beam, and what we do is we teach a conventional 5-point TCP with it. So we measure one side of the beam, measure the other side of the beam, take half. We do that in 4 different orientations and then one for the Z direction. It's different than everybody else's. Often you'll see them do it faster because they'll have like multiple lasers. They stick the torch down there and then it's done. But that's just an offset. In order to do a true TCP, you need to orient the tool in multiple directions. In other words, generating a sphere around your fixed pointer. And that's what we do with the Bullseye. So you can stand on it, move it, whatever you want, it will still get you the same result. If you take a normal or off-the-shelf device, it'll dip into there, but it will only give you the offset based on the relationship of that device to the robot, in most cases. So definitely do your research.
Still working.
Yeah,
right.
So if you'd like to see it in action, we can force an error.
Yeah, break it.
We're going to break it.
Do what my customers do to me.
So what's the biggest issue here, right? So we crash the torch. So we can crash the torch a little bit. If we crash it too much, then it becomes out of the reach, or you run into singularities or other things. So I'm going to take this torch and I'm going to move it. Oh boy, quite a bit.
That was a bad crash.
There we go, super bad crash, right? Okay. I'm going to hit play. The robot first is in this demonstration is going to run back through these 100 points, a little bit of it, just to kind of show you above the area, to show you what you have done, where that crash is. If we went into this, we would obviously crash. I'm going to step out of the light screen. And you can see just the tilt of the torch.
See, it would have hit every one of these.
And we're not going to go through full 100 points, just a couple small little paths. And we'll go through the maze too, just to show you. And then, of course, those that say, well, I don't program mazes for a living, we're going to do it on the arc plate as well.
And so I've had so many customers, they'll bend a torch, and then rather than correct it, then they'll write their next program with a bent torch. And so now they have no solution at all. So,
that's right.
You know, you've got two different programs that require two different TCPs. That's not going to work. So that's why I think this technology is so valuable.
Yeah, and what they'll do is then at the end say, oh shoot, we should have done our TCP, and then they go back to do that, and it's too late. Now they have no programs that work.
Right.
So.
Oh, been there, done that. You got to figure out which one you want to save, because you only get one.
That is correct.
So what's the next step?
Okay, so the next step is we prove that it's off. It's going to go over to the Bullseye. And we've improved the speed of the Bullseye too. So that's always been a complaint, is it would first do a quick check, then that would take about 5 seconds. And if it didn't pass, that's where the several minutes would take. With this collaborative robot, we can do it just over a minute. So if we have any other questions, it's a good time to go over, but it's going to go through 5 different orientations, and then it's going to figure out where that wire is. And then afterwards go back into the maze.
So it's that easy?
That easy.
Okay.
That easy.
Well, you keep building the cool stuff. I'll keep implementing it. And in the meantime, thanks for your help. Thanks for coming on today.
Oh, appreciate it. Thank you.